Gate 2022 Mechanical Metallurgy. For a material that undergoes strain hardening, the necking instability that occurs during the tensile testing is. So we know given sigma is the true stress and epsilon is true strain. When a material undergo tensile testing, it experiences the deformation. So the relation between sigma and E or epsilon is not is initially linear, but afterwards it is not linear. So the strain hardening or the work hardening, it is also called as cold working also, the material becomes stronger and more resilient to further deformation as it undergoes plastic deformation. So the sigma, the true stress when the engineering stress is nothing but force by initial area, force applied by initial area or load applied by initial area. But here it is force by instantaneous area. So this is A naught and this is instantaneous area. This is true stress. So considering the change, the true epsilon is logarithmic along 1 plus E. And the engineering strain is nothing but whatever the change in length or anything, final minus initial by initial. This is the engineering strain. So now the necking instability occurs when the material undergoes localized deformation like during the reduction of the cross-sectional area. This is a tensile sample and the cross-section here decreases a lot, like due to local necking. At at the point of necking, the material undergoes significant stress strain concentration. This is where the material thin outs and becomes narrower due to concentration of stress. So here d sigma by d epsilon is equal to sigma and also E is equal to n in mathematical terms. This equation implies that the slope of the stress strain curve at the point of necking is equal to the true stress which is being applied, and the material is straining to a point where the rate of stress increases matches the stress itself, indicating the point of instability. Okay, so here d sigma by d epsilon is sigma. With reference to stress intensity factor, the find the correct match of the nomenclature, mode 1, mode 2, mode 3. So mode 1 is nothing but crack opening mode, where the sample is like this. Crack will get opened and the surface moving apart from each other, causing the crack to open. This is also called as opening mode, crack opening mode. And then mode 2 is just the sliding. So the sliding happens in this way, or it can be like this also. In this mode, the crack surface slide parallel to each other with one side of the crack sliding related to another. This is also known as plane shear mode, in plane shear mode, or parallel shear mode. And mode 3, the surface will be moved like in forward shear mode. The mode 3 involves a crack surface sliding past each other with a forward shear, creating the tearing or scissoring effect. So here it's a kind of scissoring effect. This mode is also known as anti-plane shear mode or forward shear mode. So R is X, and P is Z. So it is Z by X. Sorry. Oh, sorry. R is Z, P is Z, And Q is when designing a material for high temperature applications, which one of the following characteristics or attributes is desirable for achieving the better creep resistance? To get a better creep resistance, we need the grain should be as coarse as possible. And it is also good if we have FCC crystal structures. And the high melting point is not one of the things. And cold work microstructure is also not preferable as it gives us the low or small grain size. Small grain size means more number of boundaries. More number of boundaries causes grain boundary sliding. So it decreases the creep resistance. So fine grain size also need required. So given the strain rate epsilon dot, the dislocation density rho, the dislocation velocity, which one of the following relationship is correct? Our one equation for the plastic flow of the movement is given by epsilon dot is equal to rho Vp. It is our one equation. This contribution of dislocation motion to the plastic deformation. So here it is clearly seen that epsilon is directly proportional to rho and epsilon dot is directly proportional to V. Find the correct match between the dislocation reactions to descriptions in column B. A naught by 2, 1 bar, 1 plus A naught by 2, 1 gives rise to A00. This reaction typically happens in a BCC structure. In this reaction, the half dislocations are moving toward each other, merging to form. So this is commonly seen in BCC. This is a typical uh, dislocations merging which happens in a BCC structure. If you'll see Q, A by 6, 1 bar to 1 bar, and A naught by 6, 1 bar 2 gives rise to. Here, the two partial dislocations are merging together to form a Lomer quarter, Romer quarter lock. This happens in FCC, and the common reaction which happens as they are more complex lattice structures, the dislocation are able to move and merge away in different ways. So it is 1 and R. This is the form of A naught by 6, 1, 2 bar, A naught by 6, 1 bar, 1 bar, 2. This is energetically unfavorable, but it can happen in FCC because we'll calculate B1 square plus B2 square, B1 square plus B2 square and B3 square. It is 1 by 4 into 1 plus 1, 1 by 2 is 1 by 36 into 6 plus 1 by 36 into 6. So it is 12 by 1 by 3. If you'll see clearly, B1 square plus B2 square is B3 square, 1 by 1 by 2, 1 by 3. But to become energetically favorable, this should have more energy in order to decrease its energy so that this will be formed and have a lowest energy. But here in this case, we are having B3 square as more energy. So it is 3, 1, 3, 1, 2. The quartal atmosphere, Suzuki interaction, Boschinger effect, and Nabarro hiring. The Gottel atmosphere is refers to the phenomena where Luder bands will be formed, and when the material is deformed at high strain rates. So high strains. The Luder bands are characteristic by the series of concentric bands on the surface, which happens at 45 degrees, and the movement, this happens because by the movement of dislocations under high stresses. This phenomenon is given by Franz Luder, so it is called as Luder bands. So P is 3. Next, Suzuki interaction is nothing but the segregation of the solute to the stacking fault, which is a type of plastic deformation in a polycrystalline material. So in this, the impurities alloying elements are concentrated at the stacking fault in the material, can lead to increased plasticity and improve the mechanical properties. Okay. So Suzuki will try to the segregation of the solute at the stacking faults, and Boschinger effect refers to decrease in the yield stress when loading reverse direction. So if this is the yield point, then if you try to reload it in compressive stresses, if you'll see the yield point, which should be, this is sigma in tension, this compression value, if you'll see, is always greater than this tension. The stress in tension is always greater than the stress in compression, because if you'll see, due to the loading of direction, loading and reversing it, the yield point, the yield stress itself will try to decrease. This is observed mainly in many ductile materials, and it is named by under the scientist Boschinger. So decrease in yield stress when loading in reverse direction. Nebera Haring, it is the stress which is assisted by diffusion of vacancies in the plastic deformation in a polycrystalline material. It's a type of creep which happens at high stresses, high temperature, and with low grain size, and with high grain size, means coarse grain size. So 3412. From high temperature tensile testing, the flow stress of an alloy was found to be 50 at the strain rate of 0.1 per second and 70 MPa at a strain rate of 10 seconds. The strain rate sensitivity parameter is. So we know strain rate sensitivity is given by E dot power m. This is the strain rate sensitivity. So sigma 1 by sigma 2 is equal to E1 dot by E2 dot whole power m. So ln sigma 1 by sigma 2 by ln E1 dot by E2 dot is equal to m. So ln of 70 by 50 by ln of 10 by point, okay, 0.1 is equal to m. So you get ln 1.4 by ln 100. The m is equal to 0.073. The high cycle fatigue data is given for an alloy at various alternating stresses sigma A is given. So at 500, you have seen number of cycles as 1000. At 400, 10,000. 300, it's 1 lakh, and 200, it is 10 lakh. A specimen of this alloy is subjected to multiple stress cycles sequentially in the following order. For the first 5,000 cycles, sigma A is 400 MPa, followed by 25,000 cycles, it is 300 MPa. And according to minor rules, the number of cycle that can be applied at a stress of 500 MPa. So, you know, minor rule, Ni by capital Ni is equal to 1. So if you'll see, for first 5,000 cycles at 400. So for 5,000 cycles, the fatigue limit is 10,000 at 400 MPa. and 25,000 cycles at 300 MPa, which is nearly 1 lakh, plus for 500 MPa, the number of cycles is only 1000. So it is n equal to 1. So it is 1 by 2 plus 1 by 4. So n1 by 1000 is equal to 1 by 4, which is 0.25. So n1 equal to 250. A cylindrical specimen of aluminum with a diameter of 30 mm is cold extruded a diameter of 20 mm. If the flow behavior of the alloy is expressed by equation sigma is equal to 350 epsilon power 0.3 MPa, the ideal plastic work of deformation per unit volume. So you know U is equal to integral e to epsilon sigma t epsilon. So it is 0 to epsilon 350 into epsilon 0.3 by e epsilon. It's 350 into epsilon power 1.3 by 1.3. Now, you know epsilon is equal to ln d naught by df, which is equal to ln 30 by 20. So now this is nearly, if you will put u is equal to 350 into ln 30 by 20 power 1.3 by 1.3. This is equal to 206.5 megajoules. The given the stress tensor 130, 30, 30, 50, and remaining the stresses are 0. The maximum shear stress is, for a maximum shear stress, tau is equal to, according to Tresca criteria, tau is equal to maximum principal stress sigma max minus sigma min by 2. Here, as the remaining elements are 0, you need to apply A minus lambda I is equal to 0. So it is 130 minus lambda into 30, uh, 30, 50 minus lambda, 0 minus lambda, 0, 0, 0, 0. You need to take as 0. So it is 130 minus lambda into 50 minus lambda into minus lambda. Okay. Minus 30 into 30 into minus lambda plus 0 plus 0. So it is 130 minus lambda minus 50. So plus 900 lambda. So if you solve this equation, you'll get lambda is equal to 0, comma 130 minus lambda into lambda minus 50 minus 900 is equal to 0. So lambda is equal to, on solving it, we get 160 comma 20. So the maximum 60, 20 and 0. The maximum stress, it is 160 minus 20 by 2. Is approximately 140 by 2.